Okay, so we talked about rational functions last time, and remember rational functions are literally just a ratio of two polynomials. You can have, so there's really like three things that we can find. How do you find vertical asymptotes from a rational function? Well, you just set the bottom, your denominator, equal to 0. Of course, that's after you simplify it, because if there's any factors that cancel out from both top and bottom, it's a removable discontinuity. And then if you want to find the horizontal asymptotes, there's three different, options. Either you can have the asymptote is 0, bigger on bottom. It's like, there's a saying that some of my kids last year did, like Bilbo something, whatever. Bigger on bottom, Bilbo, I don't know, bigger on bottom, 0, bigger on top, infinity. What is it?
Like bigger on bottom, 0. Mm-hmm. And then bigger on top. I don't know. Only Bobo seems to work in my head.
So more or less, if you take the leading term from the top, leading term at the bottom, and you write it as like a ratio, if you simplify it, right, so this red one simplifies to 5 over 4x squared. I mean, bigger on bottom, like it's going to be going to a really, really big number on bottom, which means the overall will be 0. Versus a horizontal asymptote, if you have the same exponent on top and bottom as a leading, like they effectively cancel each other out and they're just left with the ratio of the coefficients. So if it's the same, like highest exponent on top and bottom, it'll just be the ratio. But if it is bigger on top, well, which gets bigger faster, right? The cube term or the squared? Which gets bigger faster? Cube, right? So this one grows way, way bigger. So that means the overall number is just going to keep growing. It's not actually going to level out and approach a single number. So either you can have a horizontal asymptote that's 0, you can have a horizontal asymptote that's a number, or you won't have a horizontal asymptote. And this is the case where we'll go through today. When we talk about oblique asymptotes. And then we learned how to do intercepts already. An x-intercept is where y is 0, so you set y equals 0 and solve for x. And then the y-intercept is where x equals 0, so you set x equals 0 and solve for y. Okay, so here we want to find the domain, vertical and horizontal asymptotes, and that's it. Okay, so there's three things to find: domain, vertical, and horizontal asymptotes. So let's do this first one. Think about the domain. This is a problem that we did before in chapter 1. How would I find the domain? Exactly. So I look here. I know that the bottom can't equal 0, otherwise the whole function would be undefined. So we solve and we see x cannot equal 1. So to write that as a domain, it's literally going to be all the numbers except 1. So negative infinity to 1, union 1 to infinity. Wonderful. Check. Domain. Done. So vertical asymptotes. To find the vertical asymptotes, it's more or less the same as like trying to find the domain of a rational function. The difference is we have to make sure nothing cancels, right? There's not an x minus 1 term on the top. So it turns out that our vertical asymptote is x equals 1. That's where the vertical asymptote occurs. And then the horizontal asymptote. This one's a tad bit harder. So we just have to find the leading term. It's called the leading term test. So clearly there's only one term on top, so we pick it. But which is my leading term for the bottom? X, yeah, it has the highest exponent. So what I'm going to do for the horizontal asymptote, you literally do the leading term test for the top, and you take your leading term from the numerator and the denominator. So I take the limit as x goes to infinity of x over x, right? You just write the leading terms that way. Well, x over x is the same thing as 1 over 1. And something that we cover in calculus, and I think in chapter 12 for the juniors in May, whenever you take a limit of a constant number, the answer is just that constant number. So this is just going to be 1. So I have a horizontal asymptote at y equals 1. That's it. So roughly like what this would look like. So I know at x equals 1, I have a vertical asymptote. I know at y equals 1, I have a horizontal asymptote.
Let's see. So I could pick like one number. I could put in 0. So I have 0 over -1. So that's just -1 to find out what my point would be. So 0, -1. It looks something like this. And then you have to like follow the asymptotes. This is, when do I do this? Is it this section? I think so. I think it's sometime, maybe chapter 3 or whatever. And then I pick one other point. So I picked x equals 0, and then you can't cross the asymptote. So that's how I knew how to draw it. Just plugged in 0. And then I could plug in like 2. So I have 2 over 1. Right, so I'm plugging into this function right here. 2 over 1, so it'd be something like this. It's roughly what the function looks like. Cool. See, all I did was plug in one number to the left of my vertical asymptote to figure out which side of the horizontal I was on. Then I plug in one x value to the right of my vertical asymptote to figure out if I'm above or below the x asymptote. Sorry, the horizontal asymptote. That's it. That's a little preview of what we're going to be doing, I don't know, sometime in the future. Okay. Sorry, questions over this? Have you done horizontal asymptotes before? Yeah? So you already knew this? Wonderful. I don't know why people were lost yesterday. Okay, let's do this next one. Okay, so I need to know what is really limiting my domain, right? The 4x squared, this is a polynomial term. Like it will be for all real numbers. So really the thing that's limiting me is the denominator of this fraction. So if I set 2x squared plus 1, I know it cannot equal 0. We're just going to solve. Just get x by itself. So x is going to equal plus or minus the square root of -1/2. So think like, what does this mean? You know, what does this mean?
There's no number you can plug in that.
Hey, okay, exactly. That's good. We're ahead of the game. Okay, so there's no x value that I could plug in that would actually like make the bottom of my fraction go to 0. That's it. Forgot to take. Okay. So this is an imaginary term. It's an imaginary number. If you think about what 2x squared plus 1 looks like, it's roughly something like this. It has no x-intercepts, right? 2x squared plus 1 will never equal 0, so therefore this bottom of the fraction, it will never be undefined. So my domain is going to be all real numbers, aka negative infinity to positive infinity. What does this mean for my vertical asymptote? Yeah, I don't have one. There's none. And then horizontal asymptote. This one's a little harder because it has to be a rational function. But right now it's not totally a rational function, right? I have one term plus a fraction, so I need to make a common denominator. Okay. So if I multiply this by 2x squared plus 1 over 2x squared plus 1, I'll have 4x squared times, 2x, that's not pretty, 2x squared plus 1 plus 3 all over the same fraction, 2x squared plus 1. Because I just multiplied this by 2x squared plus 1 over 2x squared plus 1, because effectively I'm multiplying by 1, and anything times 1 is itself, so it's like a sneaky little trick. Okay, so I'm just going to distribute this guy out. 8x to the 4 plus 4x squared plus 3 all over 2x squared plus 1. Because why am I doing this? What are we trying to do? What are we trying to do? Yeah, I need the leading terms, so I can do the leading term test to find the horizontal asymptote. So the leading terms are these guys. This is effectively 4x squared over 1, which means we don't have a horizontal asymptote either. Because it goes on forever. Just keeps increasing without bound. So another way to think about this. Sorry, you guys like still reading? No. Okay, another way to think about this is as x gets bigger and bigger and bigger and bigger, right? This term just keeps growing, right? As x gets bigger, you square it, just keeps going. Versus this term, as x gets bigger, the bottom gets bigger, so the overall number gets smaller. So although this portion is like approaching 0, it's approaching smaller and smaller, this one just keeps growing without bounds, so therefore the whole function just grows without bounds. Okay, cool. Questions? I think we're okay. All right, so surprise, I just showed you how to graph up here. Now we're going to do it for reals. So graphing rational functions. Graph the following function, state the domain, show all asymptotes. So roughly what we just did, there's like 5 things we want to find, right? So I want to know what's the domain, find the horizontal asymptote if there's one, vertical asymptote if there's one. It would be helpful to have, see if there's an x-intercept and see if there's a y-intercept. So there's really like 5 things to do. And once we have all those pieces of information, it makes graphing it like super way better. Okay. So first, why don't we simplify this function? Right, because I want it to be in like factored form to see if anything cancels, because that will help me know what's going on here. So this is the same thing as saying x plus 1 over, and since the bottom is x squared minus 4, that's a difference of squares. So it's x plus 2, x minus 2. All right, nothing cancels out, so oof, okay. It's not, okay, so nothing cancels out, so I know there's no holes, no removable discontinuities. How many vertical asymptotes will we have? 2, all right, because there's 2 terms on bottom. There'll be 2 places where our whole function will be undefined. So I know that x plus 2 cannot equal 0, otherwise the whole function will be undefined. So that means x cannot equal negative 2. I know x minus 2 cannot equal 0. So that means x cannot equal positive 2. So listing out the domain, it's going to be all numbers except those. So imagine you have a strip of paper with all the numbers written on it, and you just want to cut out those places and then just tape it all back together, just without those 2 numbers. All right, so that's why we're going from negative infinity to negative 2, union negative 2 to 2, union 2 to infinity. We want all the numbers except negative 2 and positive 2. All right, so that's why I have to include the place between them, because I want to include negative 1, 0, 1. Sorry, did you have a question? I saw a hand over there. Okay. Okay, so we have the domain. Let's talk about the vertical asymptotes. So I think Jolie said we're going to have 2 asymptotes. Wonder where they are. JK, we found them, right? It's at 2 and negative 2. So at x equals 2 and x equals negative 2 are vertical asymptotes. Let's see. Let's do horizontal next. Would you guys rather me keep the same color or try to like, or is it confusing when I switch colors? Okay, cool. I'll just keep the same color. Horizontal asymptotes, you use the leading term test. So looking up at the way it was originally written. Yeah. Limit as x goes to infinity of x over x squared. And I'll be very clear, like when you're finding the horizontal asymptote, when you're applying the leading term test, you have to have this exactly. You have to say limit as x goes to infinity. You have to write the leading terms. Like, gotta have that. If you don't have a limit, then you made a different function, right? So the limit is like, oh, what are we actually like approaching? So x over x squared. Okay, well technically one of the x's like cancel, so we have 1 over x, right? This is about equivalent to the limit as x goes to infinity of 1 over x, right? Because one of the x's cancel. So if we're bigger on bottom, right, as we get bigger and bigger x's, the overall number, 1 over x, gets smaller and smaller. So what are we approaching? Yeah, approaching 0. So we have a horizontal asymptote at y equals 0. Just want to be clear about that. All right, have the domain, the asymptotes. Now, if we can, it'd be great to figure out if we have any x or y intercepts. So the x-intercept is where y equals 0. So to find the x-intercept, you set the top equal to 0. Did I skip over that? No, I didn't say that one. So the x-intercept is where y is equal to 0. So I have to set the top equal to 0, right? So I'm going to set the x plus 1 equal to 0. Because if the bottom's equal to 0, it's undefined. In order for this function, right, in order for x plus 1 over x squared minus 4, in order for this to equal 0, that means the top had to be 0. Right, so if the bottom's 0, it's undefined. If the top is 0, it's actually going to be 0. Because 0 divided by any number is 0. But if you have a number divided by 0, it's undefined. So that's why we're setting the top equal to 0 down here. Okay, so solve when we see x equals -1, so I'll have a value -1, comma 0. That's where my x-intercept is. So at -1, comma 0. All right, and then y-intercept. This is where x equals 0, remember? So y-intercept, where you cross the y-axis, so where x value is 0. So what we have to do is we just plug in x equals 0. Plug in x equals 0. Okay, so f of 0 is equal to 0 plus 1 over 0 minus 4, because 0 squared is 0 minus 4. Okay, so that's just going to be -1/4. Therefore, we have a intercept at 0, comma -1/4. Ooh, it's a lot of information. So what we're going to do is I'm going to put the asymptotes on our graph if you have not already. All right, so vertical at 2 and -2. Let me know if I need to scroll back over. Okay. Then I have a horizontal asymptote at y equals 0, so it's going to be kind of hard to see, but here we go. Roughly, you can see it. Okay, asymptote's done. We know our domain. Okay, we can't cross the vertical asymptotes. We have an x-intercept at -1, comma 0. So the weird thing is, vertical asymptotes, those are like the, oh gosh, what's a good one? Vertical asymptotes are like the 10 commandments. Like, you cannot break those laws. You can't, right? You can't cross a vertical asymptote. That's, goodbye, that's it. But horizontal asymptotes, they're kind of like, they're more bendy, right? They're like the gray area. If you have two vertical asymptotes, between these two, you can cross the horizontal asymptote. But on the outside with end behavior, that's when you can't cross the horizontal. If you're between the two vertical, whatever. Because remember, horizontal asymptotes, we found them by talking about the end behavior, right? Looking at the ends, what's going on. But what's happening in the middle, it can cross the horizontal asymptote as many times as it wants. But at the end, it has to follow it. Right? So horizontal asymptotes they're weird, right? They're rule breakers. It's annoying. Okay. So I'm going to pick a different color to draw the actual function. So I have an x-intercept at -1, comma 0, so that's right here. I have a y-intercept at 0, comma -1/4, so that's about right here. Okay. So you always want to, bathroom? Yeah. So you always want to like smooth it out. So I know these two are going to connect, and then I want to keep going and following the asymptote down. And follow the vertical asymptote up. since I had those 2 points, like you connect them and keep going. That's how I know it looks. Well, let me do it different. That's how I know it looks like this and not like that following. Because I had 2 points and the way I connect them, you see, as I was going from left to right, I was like going down, so I follow the asymptote. Right, from the x-intercept to the y-intercept, I was going down, so I had to follow the asymptote. Yeah, I know. Super weird. We crossed the x-asymptote, right, the horizontal. What the heck? Remember, that's just really about end behavior. So the parts in between are vertical asymptotes. If you have more than one vertical asymptote, oh yeah, you might be crossing it. Yeah. Okay, so now we have to figure out the rest of our graph. Right, we have a 50-50 shot, right? We're going to talk about this portion over here first. Either our graph is going to look like this, and I'll be above, or it will be below, right? Because I can't cross the vertical, and now that I'm like, this is the end, this is the right end behavior, I can't actually cross the horizontal asymptote when I'm talking about the end behaviors. So I have to figure out which side of the horizontal asymptote I'm going to be on. I just have to pick a number. I don't know, we could pick like 4, right? I just have to pick an x value that's to the right of this x equals 2 horizontal asymptote. So if I plug in f of 4, 4 plus, let's see, 4 plus 1 is 5 over 4 squared, 16, minus 4 is 12. Okay, all I really need to know is this above or below 0, 5/12. It's above, so guess what? Our graph's going to be above here. Okay. So 5/12, it's about a half, whatever, it's roughly here. So accuracy, it needs to be on the right half, right? If you draw it down here, that's wrong. But if you draw it up here and you follow the vertical asymptote, something like this, that's fine. I mean, this isn't like perfect. You graph it on your calculator, it's going to look much smoother and like, nicey, curvy, whatever. I just want to know, can you figure out which side of the asymptotes are you on? Right? Are you crossing them? Like, no, this is roughly what it should look like. All right, a little swoopy-loopy, I don't know what you call it, like a C or the C. Just want to see the arrow coming up, follow your asymptote, Okay, cool, because right, as we approach infinity, as x approaches infinity, our end behavior is approaching 0, as it should, because that was our horizontal asymptote. So I know over here, it's going to be either coming down toward it or like up toward it. I should show the screencast. Okay, I know over here on the left side, either I will be coming down this way or I'll be coming that way. I have to decide which one's right. You have 50-50 shot. So we just got to plug in a number. I can plug in like -4, right? Might as well. And I just have to figure out, am I above or below our horizontal asymptote? So, -4 plus 1 is -3. -4 squared is 16. Minus 4 is 12. Ah, this is negative, right? -3/12. Okay, so I'm below. Roughly something like this. And then once I know which side I'm on, I can't cross the asymptotes. So you follow and then you just can't cross them now. Okay. How's that? Yeah? Keep going? Okay. So we'll try the next one. Do you guys want to give it a shot yourself first? Yeah, maybe? Yeah? Try to find some of the stuff that we found, right? Domain, vertical asymptote, horizontal. I'll give you about, I don't know, 30 seconds to give it a try, and then I'll like start working on it so you can check. Because if you can do this now, I mean, the homework shouldn't be too bad. Alright, so the first thing I did was like fully factor it, just like do that right away. Because if something, so to find the domain, right, you just set all the factors on the bottom equal to 0. But with vertical asymptotes, right, if this was an x plus 2 on top, this guy would go away and then you only have 1, right? So it's kind of the difference. The places where you cut out your domain will always be vertical asymptotes. It depends. If something cancels, it's removable, you just draw a hole where it would be. So I'll let you keep working. I'll just write out the domain because it's very similar to what we did last time.
You want us to do the x-intercept.
Yeah, x-intercept, y-intercept, vertical asymptote, horizontal asymptote, and domain. Those are like the 5 things that'll help us graph it. Yeah. So remember, to find the x-intercepts, you set the top, right, the numerator equal to 0. By fully factoring at the beginning, it made it pretty easy, so just set each factor equal to 0. Notice that when we did our horizontal asymptote, the x squared more or less like canceled out. So I'll just have a horizontal asymptote at 1/2. Just trying to explain how we found each of these. Okay, how are we doing? Did we find all these? Did we start graphing it? Maybe. Nice to figure out how we found them. Like start writing, right? Showing the asymptotes. My asymptotes are always like dashed. Makes it clear to see. So do not cross. So I'll freeze this and leave it up there for another 10 seconds to make sure you had it all wrote down, and I'll just start drawing my asymptotes and stuff. Since, like, you know how to draw those, so you don't have to watch me. So the horizontal, I mean, it's kind of hard because it's at 1/2, but you can do it. Okay, am I good to go over to the graph portion? Okay, just make sure. I'm trying to make sure I don't go too fast. Because, you know, sometimes I, like, ask students, like, how was the lesson or something, and that's probably the biggest feedback I get is either I talk too fast, or I can move too fast. Okay, so I drew my vertical asymptotes at x equals -2, +2. Here's my horizontal asymptote at 1/2. Right? And then this is one reason why I wrote it like to the right. When I zoom in, I can really see my points and draw them. So here are my two x-intercepts at 4, 0.
right here, and at negative 3, 0. I have a y-intercept at 0, 3 over 2. Well, that's just 1.5. 1.5. So it's kind of nice because we don't have to plug anything in, right? We just follow the asymptotes. So this, we can't really go down, right? Can't really go down. All we do is like plug, well, I mean we could, but plug in a number, what you're going to see is it's going to go up. But I'll show you how we do that. Let's do the two easiest ones first, right? Let's do the two easiest ones first. This outside. We have a point, it's on this side of the horizontal asymptote, so we just didn't follow the asymptotes. This guy, we have a point, it's on the bottom, so we just follow our asymptotes.
The middle one's a little more tricky, so I'm going to go through it. So since we already had a point over here, so I can just follow the asymptotes. No plugging in necessary, just follow the asymptotes. Because remember, when it's like on the outsides, like you have to follow both asymptotes. Right? The flip-floppy, flaky, horizontal asymptote, it's only flaky if you have more than one vertical asymptote. It's only flaky if you're between the vertical asymptotes. If you're approaching the end behavior, oh yeah, the horizontal asymptote, it is like fully law-abiding, but... Okay, so I just have to figure out, okay, which way do we go? Let's see. So I'm going to plug in -1, right? F of -1. Let's see what we get. So I'm going to, let me move it up here. I'm going to use this because it makes it faster. I don't care what the actual value, right? I don't care, whatever. The x value, -1, I don't really need the y value. I just need to know, am I going down or am I going up, right? Is it a positive or negative? So if I plug in -1, -1 minus 4, I get -5. -1 plus 3 is 2 over 2 times -1 minus 2 is -3. -1 plus 2 is 1. So we get something like, I don't know, -10 over -6. So that's positive, I don't know, 5/3. 5/3. So it's positive 5/3. So this is the same thing as 1 and 2/3. 1.66666. Is that higher or lower than 1.5? Higher, right? So it's roughly something like right here. Cool. So since it's higher, I just follow it and swoop-dee up. I need to find a better verb. Do you guys have a better verb than swoop-dee? I follow the curve by connecting the 2 dots. Boring. All right, let's try the next one. Okay, ready? We got 50-50 shot here. Either our graph's going to go down like this, or it will come up, right? It's got to follow that vertical asymptote. All right, it's okay. We either have to go up or go down. So I'm going to plug in 1, right? Let's plug in 1 and let's find that value. So 1 minus 4 is -3. 1 plus 3 is 4 over 2 times -1 times 3. So that's -12 over -6. Oh, that's just going to be 2. Cool. So that definitely is, now we're definitely going up, right? It makes it clear. All right, so that's our graph. So you didn't necessarily have to put it at the exact point, 1, 2, what I'm looking for when you have these graphs. Do you have an upper V shape here? This one you had to find, so it should be exact, like this dot should be exact. Otherwise, as go up and follow the asymptotes, right? This dot should be exact because you found it. It's an x-intercept. Otherwise, swoop it, right? Just follow the asymptotes. Right, the one where you have to find it, you should be precise. But the rest of it, okay, right? You kind of squint your eyes, and I look at everyone's papers. All of the graphs look the same. That's all I want. All right, now for our favorite oblique asymptotes. Ooh, actually, I'm trying to think if I skipped this last year. Okay, we can do it. I know I don't put on a test for you, so You know what? No, I'm skipping it. Because we don't. It's useful, but also cool. Honors does it. We don't have to. That's one thing I can cut for you. Because we have a lot of stuff. Wonderful. Okay. So, when the numerator and denominator have common terms which can be eliminated, removable discontinuities called wholes can appear of the common factor. Okay, this is what I was just saying, right? This is why it's so important to start by factoring and then simplify. This is what people missed all the time on the test last year. It broke my heart. Like, please, factor first, okay? Then see if anything cancels. If it cancels, it's a whole. If it doesn't cancel and it's on the bottom, it's a infinite. All right, so I said it like a bunch when we were studying domain. Do you remember that? I remember. I said it like 100 times. All right, this is why. All right, let's do this one. So, that's what we just did. All right. All right, we're finding the domain, vertical asymptote, horizontal asymptote, x-intercept, y-intercept. But now, I mean, surprise, I just told you about holes. We're going to have a hole, and then we should find the coordinate where the hole is. That way I can literally draw a circle. Okay. Cool. So, first thing I'm going to do is factor this guy out. So I have x plus 3, x minus 2, 3. Oh my god. X minus 3 on the bottom, x plus 2. It's been a long day. Alright. Notice that guy cancels out. The x plus 3 cancels out. So clearly, cancels, that means whole. What?
It's x minus 3.
Yeah, it's the one I canceled, right?
Yeah. You said x plus 3.
Yo, I'm sorry. That's awkward. Yeah, x minus 3 cancels. I was like looking. Okay. Okay. Yeah, the minus 3 cancels. Whole. At x equals 3. Because when you set x minus 3 equal to 0, you get 3. Okay. So, let's start with our domain. So the domain, for the domain, you just look at the bottom. I know x can equal 3 and x can equal negative 2. Alright, you just look at these bottom two. X cannot equal 3, x cannot equal negative 2. So I'm cutting that out. Negative infinity to negative 2, union, negative 2 to 3, union, 3 to infinity. But, so normally we would say, oh yeah, vertical asymptote, right, at x equals 3 and x equals negative 2, except, nope, that's not the vertical asymptote because that is where our hole occurs. Don't be deceived. Don't be deceived. Okay. Maybe I shouldn't even wrote that. I just want to make it clear that, like, nope, that's where our hole occurs because that's where it cancels. Alright, now let's try our horizontal asymptote. Do you guys want to give it a shot before I write it? Yeah. Alright, give it a shot. Yeah, horizontal. I think that's the best arrow I've drawn in my life, and I'm never going to go back. That's it. Actually, it's not even that good. So the horizontal asymptote at y equals 1. So to find the y and x intercepts. So our x-intercepts, we would think, would be at 3 and negative 3, but JK, 3, remember, is where our hole is, so it's not actually going to be an x-intercept. What we have to do is we have to plug into the reduced equation. It's like finding the limit at that point. So we've done this before. So that's like, normally we do the 5 things: domain, the 2 asymptotes, the 2 intercepts. But now we have to actually find where is the hole? We know we have a hole at x equals 3, but what's the y value of the hole? So this is, I don't know, I think this is the hardest part of this whole problem, right? We have to find the y value at the hole. Because I want to know xy coordinate, where do I draw my little circle, my little donut? So what we must do is plug into the reduced equation. So reduced equation means after we cancel out the factor, right, where we found the hole. So we're plug in x equals 3 into, all right, let's see what canceled. So we had x plus 3 over x plus 2. All right, this is the reduced equation. Because we cancel out the x minus 3 on top and bottom, this is what was left. So this is where our hole is going to occur. This gives us our exact coordinate of our little donut. Okay. All right, so
Why are you complaining for the reduced equation?
if we plug it into the original one, it'll be 0 over 0. Because if you plug in x equals 3, you get 6 times 0 over 0 times 5. So you get 0 over 0. Because it's technically it's not defined at x equals 3. That's why we're not going to put a point, we're going to put a hole. But it's not exactly undefined, it's indeterminate form. So remember, if you have 0 over 0, it's called indeterminate, because we can't determine, is it an asymptote there, is it a hole, what the heck is going on? Yeah. Okay, so let's draw everything. Vertical asymptote at -2. Probably change the number so it's not just -2 all the time. Horizontal asymptote at 1. Then y-intercept is 0, 3.5. 3 over 2, so it's right there. X-intercept at -3, 0. We have a hole at 3, 6 fits. That's just a little over 1. So 3, a little over 1 is right here. It's a hole. And then we're good. We only have one vertical asymptote, so we know we have to, the horizontal asymptote is going to be a fully law-abiding citizen. Since there's only one vertical asymptote, we can't cross it at all. So over here, we already figured out which side of the horizontal asymptote we're on because we had that x-intercept. So you follow the asymptotes. You can't cross them. You get close, just don't cross them. Same here. Follow. Oop, look at my hole. There we go, right there. Alright, are we good on this one? Don't wanna rush you, but I'd like to try the next one. Next probs. So, that's how you graph them, but how do you actually solve rational equations, rational functions? To solve, you multiply each term in the equation by the LCD, least common denominator, of all the terms of the equation, and then be sure to check for extraneous solutions. So I think we can get through at least A before we have to be done. Oh yeah. So, for instance, solve the following functions, state any restrictions, check for extraneous solutions. So what's the least common denominator here? Yeah, x minus 6. Are there any restrictions? What can x not equal? Yeah, x cannot equal 6. That'd make the bottom go to 0. So what I want to do is multiply every single term by x minus 6. I mean, technically I'm multiplying the 0 by x minus 6 as well, but I mean, that just goes to 0. So this guy totally cancels out to make sure to distribute the x. I forget, have you guys done this before? Maybe in Algebra 2? I don't know. Nothing adds to negative 6 and adds to negative 4. I'm sorry, multiplies negative 6, adds to negative 6. Multiplies negative 4, adds negative 6. Like, even negative 4 and 1. Wow. So, we gotta use the favorite quadratic equation. Negative b plus or minus b squared minus 4ac all over 2a. Because we're trying to solve for what x equals, right? We're solving rational. You solved quadratics before. This is how you solve rational. So, 6 plus or minus 36 plus 16, 46, 52. Yeah, square root 52 all over 2. 52, there's 52 cards in a deck. How many suits are there? 4, okay. So 4 times 13 is the same as 52. And 4 is a perfect square. So this is just going to be 6 plus or minus 2 root 13 over 2. And then we can simplify a little bit. 3 plus or minus root 13. Neither one of those, right? That's not 6. Neither one of those are equal to 6. So both of those are my solution. The issue is, if one of our answers was 6, nope, just kidding, that actually can't be a solution, that's extraneous. Okay, so it's a good start. We'll finish this next time. I think it'll take like 6 minutes for the rest of these. It's not too long. Okay, see you guys tomorrow.